Let me hit you with a fact. The mass of a nucleus is less than the combined mass of its constituent nucleons. Why is this so? Stay tuned to find out.
How to bind, fuse and fizz with regards to binding energy, nuclear fusion and nuclear fission. Start with binding energy. To completely understand binding energy, we need to also understand Einstein's most famous equation, E equals mc squared. The actual logistics of the equation isn't important, but what we do need to understand is that energy and mass are really two forms of the same thing. So energy is mass.
Okay, we'll now link E equals mc squared to binding energy. So first, for definition, what is binding energy? Binding energy is defined as the work done on a nucleus to separate it into its constituent neutrons and protons. So I'll give an example about how this links to E equals mc squared. Imagine a nucleus. Here in the nucleus, the binding energy is a maximum and the potential energy equals 0. If you were to separate these protons and neutrons, the potential energy increases as you move further away from the nucleus. So, the equation E equals mc squared, if the potential energy increases, the mass of the nucleons will also increase. Hence, the mass of the separated constituent nucleons is greater than the mass of the nucleus itself.
You know what this video has been missing? A bit of maths. So let's do some. To start with, U, atomic mass unit, 1.66 times 10 to the minus 27 kilograms. That represents 1/12 of a carbon-12 atom. The mass of a proton, in terms of U, is 1.00728. The mass of a neutron, in terms of U, is 1.00866. And the mass of a helium nucleus is 4.001504. Remember, that's got 2 protons and 2 neutrons in. Now what we're going to do is work out the binding energy of the helium nucleus. So to start, we need to add together the masses of the constituent nucleons. So we have 2 protons plus 2 neutrons. And that equals 4.03188 U. The next stage is to work out the mass deficit. To do that, we need to take this, the mass of the helium nucleus, from the mass of the constituent parts. When we do that, we get 0.0303 U, that being atomic mass unit still. From then on, we need to convert this into kilograms. So that's 0.0303 U multiplied by the atomic mass unit, 1.66 times 10 to the minus 27 kilograms. And when we do that, we get 5.03 times 10 to the minus 29 kilograms. Right, so we're going to work out the binding energy. We're going to take this, the mass deficit, which is the difference between the masses of the helium nucleus and the masses of all the constituent parts, and put that into Einstein's equation, E equals mc squared. So the binding energy will equal the mass deficit multiplied by the speed of light squared, which comes out at 4.52 times 10 to the minus 12 joules. The next stage is to convert this number into electron volts. So we do that by dividing it by the charge of an electron, 1.6 times 10 to the minus 19. When we do that, we get 28.3 mega electron volts, mega being times 10 to the 6. That represents the total binding energy of the nucleus. Now there's just one more stage to go where we divide the total by the number of nucleons to get the binding energy per nucleon. This is a really important number as it represents the binding energy per nucleon, and this determines how stable the nucleus is going to be.
Okay, so here we can see a graph of the binding energy per nucleon against the number of nucleons in the nucleus. So, we can see that as the number of nucleons in the nucleus increases, the atom gets more and more stable, i.e. the binding energy per nucleon increases. This happens up until iron. Now this tells you that iron is the most stable element in the universe. Because after iron, you can see that the binding energy per nucleon slowly decreases. Okay, so the elements on this side of the graph most readily undergo fusion because when they undergo fusion, they release energy. And on this side of the graph, the elements most readily undergo fission because when they undergo fission, they release energy. Nuclear fusion and nuclear fission will be later explained in the video.
Nuclear fusion takes place when two smaller nuclei combine to produce a bigger nuclei. Energy is released in the reaction because the binding energy per nucleon is higher in the bigger nucleus. Nuclear fusion takes place all the time in stars. In the main cycle of a star, hydrogen and helium, some of the lightest elements on Earth even, are combined to produce a larger nucleus. This fusion cycle continues for a long time throughout the star. In the death of a star, big stars, supernova occur, and all the heavier elements present throughout the entire universe were made during that process. Due to the immense heat and energy, the heavier elements were able to fuse.
So, you know what this video needs? It needs some more maths. Look what we got here. We've got photon-photon fusion. When two photons collide, you get a hydrogen atom, a positron, which is the antiparticle of an electron, and you also get energy released. And we shall try and work out how much energy is released. So, first of all, we'll work on the total mass before the fusion takes place. So, since we have two photons, the total mass is 1.00728 U plus 1.0072 U, and that comes to 2.01456 U. Okay, so now work out the total mass after the collision. So the mass of a hydrogen atom is 2.01355 U plus the mass of a positron, which is 0.00055 U, and that comes to 2.01410, all in my head. So, we work out the mass difference between from the start of the reaction to after the reaction. So that is 2.01456 U minus this number, 2.01410 U, which comes to 0.00046 U. So, with this number, we'll first convert it to kilograms. So see as though U is 1.66 times 10 to the minus 27, we do 0.00046 times 1.66 times 10 to the minus 27, and that comes to in my head, 7.636 times 10 be minus 31 kilograms. Okay, with this number, this mass represents the total energy released when using E equals mc squared. So we use E equals mc squared. So we do E equals 7.636 times 10 to the minus 31 times the speed of light squared, which comes to, once again in my head, 6.8724 times 10 to the minus 14 joules. So to make this into a more comprehensible number, we convert it to electron volts. So we divide that number. Wait, shall I go up there? Would that be easy? I think it'd be easy. So we divide that number by the charge on an electron, which is 1.6 times 10 to the minus 19, which comes to 0.4 mega electron volts. And that is equivalent to the energy released. So we can see here why nuclear fusion releases energy.
Nuclear fission is when a large nucleus, for example uranium, is split by a slow-moving neutron. When we say split, we don't mean like a breaking pull. What really happens is that the neutron is absorbed and then everything, the products of the fission, are given off. The two main products are two approximately equal fragments. For 235 uranium, we have barium and krypton. Another product is two neutrons. These are called fission neutrons, and they lead to chain reactions in places like nuclear power stations. Another product of nuclear fission is energy, because there is a higher binding energy per nucleon for the two smaller fragments than there are for the larger fragments. Some examples of nuclear fission are, as previously mentioned, the nuclear power station and the nuclear bomb.
So, keeping the theme of this video, we're going to do some more maths, eh? How about it? So, what we're going to work out is just the amount of energy released in the nuclear fission reaction. So, the energy released is equal to the difference in the binding energy of the uranium-235 and the barium and the krypton. So that's what it's going to be. So looking at the graph, that's the binding energy of per nucleon of a uranium atom. That's the binding energy of barium per nucleon, and that's the binding energy of krypton per nucleon. So if we do these sums to find out the total binding energy in the nuclei, we get, for the first one in my head, as always, you know, I'm running theme for this video, 1783.65 mega electron volts. For barium, we get, again, in my head, 1267.2 mega electron volts. And for krypton, we get 765 mega electron volts. So, to find the difference, what we do is add up the total binding energies of barium and krypton, which comes to, so, minus 765, and that, sorry, plus 765, and that comes to 2032.2 mega electron volts. So, if we find the difference between this, between the total binding energies of the barium and krypton, i.e. this number, and the uranium atom, the energy released equals 249 mega electron volts. The total binding energy values means that nuclear fission produces a large amount of energy. 1 kilogram of uranium-235 produces 8 times 10 to the 13 joules of energy, which is 1,000,000 times more than 1 kilogram of oil or coal produce. Well, if you got to this point in the video, well done and thank you for watching. You now know how to bind, fuse and fizz. Probably. Actually, maybe not. You best watch Brian Cox. We may have caused some confusion. See you later.
This can go in the outtakes. Oh, you're still filming.
Hi, it's Alex. So good.
From then on, we need to transfer. Oh my god.
Alex in the house, you know that? Alright, okay.
Which is a really important number, because that decides relative. Oh no! I'm so close!
It's like you...
Here is an analogy for nuclear fission. Here is an analogy for nuclear fission. The rest. Right, no.
Okay. Just that. So...
Here is an analogy for nuclear fusion.
Okay.